Thanks to SBM for hosting today. So my name, Glen Manning, I'm a landscape architect. I work for HTFC Planning Design, and my background in green infrastructure is we've done several projects here in Winnipeg. We've done a little bit of background studying here at the office. I'm a green roof professional, and but it is an area that we are growing and continuing to learn about. So just want to let you know it's a pretty broad topic. It's something that we'll be just scratching the surface on. Hopefully I'm looking through the names here that I'm going to hit the right level of kind of introductory versus advanced stuff, because you see there's quite a number of practitioners that some of this might be very familiar to all of you. So I'm just going to share my screen and launch the thing. Go. Okay, I think we're good to go. So I'm just going to move you folks over to the other screen so I can see it. And then we're good to go. I do have a glitch here. Oh, that works. Okay. I just had to get you out of the way of my my script. All right, thank you. So as I said, this is a vast topic. The plan is I'm going to show you a few local examples, and we'll talk in general about 3 or 4 most important green infrastructure technologies, and we'll polish it off with talking about some strategies to try and get this into the mainstream. So the term natural infrastructure covers a whole set of practices and concepts, and they're called by many names. So I'm likely to be slipping back and forth between using the term natural infrastructure and green infrastructure. But as you can see by this list, there's, half a dozen more, lots of acronyms. One I like in particular is the one at the bottom there, the SUDS one, because it has kind of a water and cleaning side to it too. That's a pretty popular one right now. But it includes generally, all these things describe in general a range of techniques that are mostly centered around managing stormwater. They also include things like soil stabilization, thermal regulation, and food security. So it's not quite in the mainstream yet, but it is definitely gaining prominence. I assume most of you on this call have heard of it before, heard of green infrastructure before, but it's still a bit of a slippery concept. So one of the documents I was looking at had done a study of 122 different city plans from around the states. And they found that 57% of those plans had different definitions of natural infrastructure. And within those definitions, there were 150 different ones too. So some of them were repeated, obviously. And then even more surprising is there were 693 different green infrastructure practices that were collectively described as green infrastructure. And those ranged from things like green energy to bike-friendly streets. So I think part of the problem is the term green, which we all associate just with general things that are sustainable and help the environment. So we're tending towards using the term natural infrastructure more frequently now to help with that. But it is a problem either way you look at it, because the more this term moves away from describing a set of practical tools toward some kind of umbrella term for any miscellaneous innovative planning practices, that's going to tend to undermine the ability for us to deliver on the promises. So therefore, picking the right definition is important. And as I was combing through the internet in various places looking for a really juicy one, this one I think covered best what I want to talk about in this presentation. So that is that green infrastructure is an interconnected network of natural areas and open spaces, as well as technologies and practices that use natural systems or engineered systems that mimic natural processes to enhance the overall environmental quality, conserve ecosystem functions and natural capital, sustain clean air and water, and provide social and economic benefits to people and communities. So there's a lot there, but the main ones are the ones that I highlighted in that light green color. And that's the idea of interconnectedness, and that there's this biomimicry that's a large part of the practices we're going to be focusing on today. The main idea behind natural infrastructure is to harness nature to do some of the work of gray or hard infrastructure. Instead of relying on things like sumps and catch basins to catch debris, or pipes to conduct stormwater to centralized treatment facilities, we want to use plants and soil to contain, degrade, and eliminate pollutants right near the source, slowing down storm peak flows or storm flows at their peaks, and using a large portion of the water on site productively to nourish the plants and recharge groundwater. So it sounds pretty simple. And I'm going to share ways that natural infrastructure can substitute, safeguard, or complement these engineering infrastructure. So it's not necessarily instead of, it's more on top of right now, typically. And most of these ways have been, over the last 10 or 15 years, proven effective and cost competitive, and they offer multiple benefits beyond the strict engineering functions. I first came across this idea of engineering with nature when I was working for the Manitoba Natural Society. It was a urban stream restoration project called Naturally Clean Rivers. That was around, was about 1985, I think. I just started working on my master's degree in landscape architecture, and we were researching ecological restoration methods around stream bank stabilization. And I found these really interesting German articles on something called soil bioengineering, which combined plant material and more traditional engineering methods to control erosion, sedimentation, and stabilize the banks. This drawing on the screen right now is a vegetated riprap, where live willow stakes are driven into joints between, riprap boulders, combined in this case with brush layering and willow bundles laid underneath the stone. The city of Winnipeg actually experimented with this process early 2000s, right around the time we were building the Provencher Bridge. And we looked at including that as the stabilization for the bridge as well. But I think the area where the test was right near where Mir Hotel is right now. And as far as I know, it was a success. What struck me about the soil bioengineering idea was the sophistication of the understanding of how plants can be seen as engineering materials. This diagram is a chart. This is from a study commissioned by the BC government that includes the tensile strength of roots for various plants and allows the geotechnical engineers to accurately estimate the contribution of plants to soil stabilization. So it really was looking at plants as part of a science with predictable and repeatable results. And I mention this because in order for living systems to gain the status of infrastructure, which is really the overriding goal of this presentation and what we're trying to achieve through this movement, we need some rigorous science and predictability, and that's absolutely fundamental. The same evolution happened with hard building materials in the late 1800s and ushered in fantastic new possibilities in architecture and engineering. We need to think about plant material the same way, in terms of its performance, its properties, so that they can become tools we can rely on with some confidence. So around that same time in the kind of mid 80s, when I was working for the naturalists and going to university, become a landscape architect, the area's environmental movement was still largely focused on halting pollution and habitat loss and instilling this idea of a land ethic. So we were essentially saving nature from humans. Today, I would say that's pretty much flipped upside down, and we are more desperate for ways to save humans from nature, particularly the disasters and extremes caused by climate change. Now, it's pretty clear that this audience understands the reason that we're worried about these things, so I'm not going to go into them here, but I can say that some of the most promising tools to better protect ourselves and create more livable cities in an uncertain future, those rest in the realm of natural infrastructure. So maybe a bit of a gloomy note. I'll switch now gears to talking about what natural infrastructure is and how we can describe the various practices. So I've just taken the effort to divide into 5 main categories. The first is bioretention and infiltration, which for many, and we look at those 150 definitions we talked about earlier, that's really the meat and potatoes of most people's impression of natural infrastructure. And those are practices like bioswales, rain gardens, constructed wetlands, and permeable paving. Second category is living architecture, which combines green infrastructure practices with buildings. So that's things like green walls and green roofs. The third is functional tree planting. I had originally called this afforestation and reforestation, but it's a little more than just the idea of the urban forest. It also takes into consideration other plants of different sizes. So it's essentially functional plantings. And those would be things like urban forest, shelter belts, bioengineering, anything where we're using trees and plants for their shade, wind buffering, and soil stabilization possibilities. These last two categories are not always included in lists of natural infrastructure, but I think they have a place because they are tapping into natural processes. So the first one is water harvesting, which treats rainwater as a resource rather than a waste stream. And the second is productive landscapes, which utilize the productive functions of urban plantings to improve food security, and they can provide other benefits like pollination. We're not going to have time to talk about all of those, so I'm just going to focus on a few. We'll talk about green roofs. We'll talk about rain gardens, bioswales, and some other infiltration techniques. And we'll talk a little bit about functional tree planting. We're going to start with green roofs. And the reason we're starting with green roofs is because even though different forms of green infrastructure have been practiced around cities for thousands of years, this modern sense of what green infrastructure is started with the green roof movement in Europe, and particularly in Germany in the late 60s and early 70s. It's exploded in popularity since the year 2000. And in places like Stuttgart, 22% of all urban roofs are green. In North America, it's seen double-digit growth for the last decade. And just prior to the pandemic, I think Toronto inched out Chicago and Washington as the city with the most number of square meters of green roof installed. So it's definitely a growing consideration in a lot of major cities. Locally, acceptance of green roofs has been slower. There's a handful of really great projects out there. Here's a few of them up on the screen. There's another one. I don't think I have the Grand Beach one included here too. There's one from Birds Hill Park as well. And there's also the Sergeant Tommy Prince place on Sinclair that has a nice green roof. But overall, I'd say pretty slow take up relative to some of those cities that's booming in the green roof industry. So what is a green roof or a modern green roof? This diagram shows an inverted or protected membrane roof. This is the ones that I've worked on have all been in this format where the insulation is above. I guess the main thing to think about, like most of the systems, there's proprietary systems, there's custom-made systems, there's intensive and extensive, all sorts of variations. But the fundamentals are this, that there's a plant layer, there's a drainage layer, and then there's means of protecting the roof membrane and structures from the plant material above. But the important thing to know is that it's not just a matter of piling soil over the membrane. It's really a carefully engineered system that's engineered for lightness and drought resistance. It's actually a great example of biomimicry, taking the drainage and fertility functions of soil and exploding them into modular product layers that can be purchased and specified and controlled. So when I was working on the Manitoba Hydro green roof, I took some courses and I was able to hear from both roofers and from horticulturists on their perspectives on how green roofs work and what the pros and cons are. And I'd say from the roofer's perspective, it was a bit of a head scratcher. Lots of people were there because they were in cities like Chicago, and the courses are actually in Chicago, and they were there because there's all sorts of demand for it. But when you look at what roofers typically do, which is look for lightweight, low-cost solutions that are durable, we were doing almost everything wrong. We were adding weight, adding cost, adding complexity. We're intentionally holding water on the roof. We were restricting access for repairs and restricting the ability to trace and repair leaks. So they're a little bit of a puzzler for them. On the other side, the horticulturists were seeing the green roofs as a really tough place to grow things. So the plants are exposed to hot, dry, windy extremes. There's limited access. The soil depth has to be limited because of how much weight capacity or how much structural capacity there is in the structure below. It adds a lot of cost. and has unpredictable interactions up on the roof, particularly wind. It tends to swirl around and get deflected around by the buildings in ways that are very difficult to predict. And of course, the access is limited to monitor, maintain, and even enjoy these spaces. So on top of that, there's also the fact that up to 1 in 5 green roofs fail completely. The reason they fail is typically because of leaks, poor plant choices, wind damage, and occasionally, like this example, it was a structural problem where I guess what happened here was it collapsed because the drainage system froze. And so it was holding the water and the weight and couldn't do it. And then there's the cost. This green roof in San Francisco, that's about a $3.4 million premium over a conventional roof system. So given all that, why would anybody invest in these risky and potentially troublesome systems? There's lots of benefits, both private and public, but the main drivers are really prolonging the membrane life, which can be up to twice the lifespan, and reducing stormwater flows, which in big cities can save the big fees for new development and allow larger developments to fit into smaller footprints. Stormwater management benefits are usually the impetus for green roof legislation in places like Toronto and Chicago. And builders are often given incentives in places like that, like things like density bonuses to offset the green roof costs. So the stormwater benefit is pretty substantial. This graph shows, if you can understand what we're showing here, there's a time axis on the bottom, and there's the amount of stormwater runoff from the vertical axis. The blue line is a conventional roof, and the green line is a green roof. So there are three critical effects through creating this storage on the roof. The first is that it's delayed runoff. The second is reduced rate of runoff, and the final is a reduced total volume. So if you want to get even better effects, then you just add more soil and include thirstier plants. In Stuttgart, it was really air quality and urban heat island that spurred the surge in green roofs. Stuttgart is in a valley, so it's prone to the urban heat island dome effect. You get this kind of dome of hot air that would sit there, and smog was a terrible problem. So they were counting on green roofs as a way to help with air quality. And to all accounts, it looks like they've been successful with that. And of course, we can't ignore the importance of image. Green roofs are easily the showiest of all forms of green infrastructure, and it's a great way to share the client's appetite for innovation and their environmental values. This is the Hydro building again. There's a lot of the most important meeting spaces and the prime lounge spots all showcase the green roof to take advantage of that lovely view. One of my favorite forms of green roofing is growing food crops. This is really one of the best ways to wring even more value out of the green roof investment. And it doesn't have to be fancy. It can be pretty low key. This is a photo of the herb garden at Deer and Almond, just on the right next door to it. They're very easy to install, easy to move around, and herbs are particularly well suited for these hot, arid conditions that you find on a roof. And if you were to combine this, say, with some bees, then you've got a great little natural ecosystem going on your roof. Okay, let's switch gears to the next topic now, which is bioretention. Bioretention is using plants and soil to treat and infiltrate storm water runoff. Pretty straightforward. And like green roofs, there's lots of benefits. A lot of the benefits overlap. So the foremost are really the reduction in infrastructure again, and also improvement of water quality and reducing atmospheric carbon, in addition to several other ones we won't go into. So taking a closer look at that stormwater effect, very similar again to the green roof, that there's that delay. But you can see overall that's the green line here is the one. Can you see my cursor when I move it around here? Is that showing up? Yeah. Okay, so that green line is the green roof one. We're comparing 4 different conditions here. So this is post-development. This is what it was like pre-development. Here's a traditional control systems and LID, which is green infrastructure, shortens it up, reduces the overall volume and intensity of the effect. So with green roofs and with bioretention, all of this means, all of these graphs really just tell us that there's going to be less chance for erosion, less frequent combined sewer overflows, better ability to store the water on site and meet the requirements for whichever jurisdiction you're in for stormwater management and detention. And in some jurisdictions, it'll allow fewer and smaller pipes. So that's the quantity story. The quality story is also interesting. So bioretention takes advantage of plants' ability to remove, detoxify, and immobilize environmental contaminants. These processes are called phytoremediation. Some contaminants are modified and transferred into the air. That's that little arrow on the top of the diagram. Some of them are held within the plant, and some are sequestered in the root zone at the bottom. Soil organisms also play a role in this. But it's a big part of almost all of the practices. Anything that's got plants in it in these practices we're going to be talking about will be practicing some phytoremediation effects. And the carbon story with all natural infrastructure that involves plants is similar. Carbon can be sequestered in the soil. It can be sequestered in the biomass of the plant itself. That's the plant body, leaves. And through good management, there can be reductions in the emissions from the material production, installation, and repair. So for example, the embodied carbon that would be in the concrete pipes that we'll be putting in, that goes away when we're looking at reducing the size or eliminating the need for those pipes. And the better we do at creating a resilient system, the better this carbon is going to stay locked up in those plants because they're going to live and recycle and create an enduring community. Okay, let's talk a little more about rain gardens. So of all the bioretention solutions, rain gardens are the simplest and least expensive to construct. The only requirement really is space and soil and plants. The basic principle is to dig a depression, you dig a pit. The depression is usually not very deep, maybe 3 to 8 inches deep, and it has 3 zones. There's a buffer zone on the outside, a sloped zone, and then a flattish base. And you plant different species suited to the moisture regimes of each of those layers, with the thirstiest plants residing at the bottom. We installed one of these at the old Grace Housing Co-op in the Wolseley neighborhood. Based on the stormwater calculations, we were required to retain about 150 cubic meters of underground storage, of stormwater on the site. And most of that was achieved through burying underground kind of retention tanks. I think they were little culvert type units. But some of the perimeter runoff was picked up by the rain gardens at the corners of the property. Note this drain pipe at the bottom. You can see that little section down there. That's actually a requirement because of our really impermeable soils. It runs around the perimeter of the property and empties into one of those linear underground storage tanks in the courtyard. And then when that tank fills up, it outlets into the land drainage sewer. In more permeable soils, if we weren't building this on the prairie gumbo, then these rain guards could just infiltrate directly into the subsoil, and they're a much simpler and less expensive practice. This is a quick diagram of the Niagara Trail rain garden. This one had a number of sponsors, and one of them was Save Our Seine. I think I saw there's a Save Our Seine person on the line. So hello, hey, Ryan. Yeah, so interesting project. So we were involved with that one. There was kind of a nice promo piece around it as well. When we built this, it was a very, let's say, ambitious project. It was more than just rain garden that was intended to happen here. So we tried to include some pollinators and more seasonal variation and create this great showpiece for a number of things. And it turned out that wasn't necessarily appropriate plant choices for the moisture regimes. There was also some rethinking that was required around the inlet and weirs because we were getting silt accumulation. So I understand, and Ryan, you could tell us that this has been redone recently, right? Replanted, I think.
replanted a couple of times. Yeah, one of the original activists had a certain vision for the type of plants, and then that was rethought later. That was at least 3 years ago, but yeah.
Yeah. Yeah. So it's another one of these cases where, I mean, we're always learning every time we do one of these things. Well, there's lessons, and we're just in a continuous state of improvement and refinement. The next item we're talking about is bioswales. So what's the difference between a rain garden and a bioswale? Really just one thing, it's movement. The water in a rain garden is essentially trapped in a cavity, and in a bioswale rather, we're looking for that water to move longitudinally along the feature. So they have a slope from the source to the discharge point, and they will still hold and infiltrate the same way, but we're expecting the water to kind of drift along that axis. There's actually many types of bioswales, but three of the most common ones are grass channels, which are similar to a conventional drainage ditch, but they'll have a flatter side slopes and flatter slope longitudinally. So the water is going to be more likely to sit there, and there'll be more chance for it to work into the soil, and that the soil organisms do their business on it. Wet swales, the middle version is a wet swale where the expectation is that there will be some shallow water within it. So it's almost like a linear wetland. And then dry swales are a biotreatment that uses soil rather than plants. So that's the one on the far right there. You can see it, and it's a kind of a dry riverbed. So there's an underdrain system in there, and it's using the soil biology to do the treatment. A project where we used some of these was Clear Spring Middle School. That's the whole site had just 2 catch basins. That's what these yellow circles are. And we used a network of swales to move the water around the site and deposit it in areas where the majority of the runoff could either be filtered or infiltrated before it reaches those points. Of course, there were some challenges getting it to work. There were some errors in construction. Some of the grading led to areas that were being charged with more stormwater and for longer periods than we'd anticipated. And that led to some of the plants drowning out. Some of the culverts got clogged too. So there was more sediment moving through there, especially during the establishment period. Those problems, to my knowledge, have been remedied, and things are functioning as they were designed to do. And when we think about incorporating things like bioswales and rain gardens, we need to remember too that there's a qualitative side to these practices as well. And it's really fantastic to see how this biodiversity adds a layer of richness that enhances any kind of learning environment or urban space. So as a place for kids to hang out and learn from, it's really next to nothing. Okay, just a couple of quick slides about permeable paving. So permeable paving isn't bioretention, but it is another infiltration technology, and it consists of unit pavers designed with wider gaps. So those little gaps, they're slightly larger between here, and they admit water into open graded aggregate underground. It's not using plants, as I said, but the soil processes help, and is actually helping to recharge the groundwater reserves as well. This also is another one that's been slow to be adopted in Winnipeg, and that's again due to our soils. It makes a lot of sense to do this kind of thing where that water can infiltrate directly into the soil, but we're essentially creating a reservoir beneath these paving systems and finding outlets for that too. So it's adding quite a bit of cost and complexity. We have used it in the Exchange District in a few spots. So here's an example. So in John Hirsch Way at the end of that system, as it was just coming out towards the roundabout at the end of Bannatyne, we had to reconstruct that whole area. There was a nice row of existing basswoods, and rather than try to install soil cells or some other way to contain the roots, the decision was to see if we could pave over them with a porous paving system that would allow air and water to infiltrate down into the root system and still give the trees what they need and provide a surface to walk on. So the good news is that those trees have all survived, and they seem to be doing really well. It's just out the back door of our office here, so we can watch them pretty closely. I'm going to end this section on bioretention with a case study from Mississauga. This is from the Peel district in Ontario. Peel is like the mecca of green infrastructure projects and resources, and I would encourage all of you to look it up. There's just a whole range of them. This particular project at Elm Drive was pretty straightforward. It consisted of a row of permeable pavers, which was under a parking lane. And then next to it in the embankment, they had a rain garden. It's actually had a bit of a slope to it. So it was actually a bioswale. It's done about 10 years ago. And like all the projects they do in that area, this one had really great empirical data on its performance. And there's long-term monitoring of precipitation and discharge quantities right after it was built. The results were pretty impressive, definitely beyond what was expected. There's little to no runoff from 90% of all events, and 88% of the total suspended solids are removed. So, those are really impressive numbers. In light rains, no water at all leaves the system, and most rains in the range of 90% are light rains. So we're kind of blocking it, using it right on site. The other thing they tested for was, and this is one of the questions when I did some courses on this, was what happens to all these contaminants that are being accumulated in the soil? Does the soil become more toxic? And so they were testing and looking for evidence of accumulation and didn't find any. So they're showing that the plants are really phytoremediating up a storm. Most studies show that bioretention is less expensive than conventional gray infrastructure solutions. These numbers are from the EPA and the Environmental Protection Agency in the States. They found that rain gardens cost about 42% less over their life cycle and reduce environmental impacts by 62 to 98% compared to conventional gray infrastructure. And that's specifically related to mitigating combined sewer overflows. For the carbon numbers, we've been using an app called Pathfinder from the Climate Positive Design Organization. I don't know if any of you folks on the call are familiar with Pathfinder. It's a free tool, and it's used to assess sites and compare the emissions to the sequestration for various materials and planting and site operations. And that allows you to determine the number of years to carbon neutrality for a particular project. This was for a Winnipeg site. And our first run through wasn't all that great. We had an asphalt parking lot, minimal planting, and it resulted in a 177-year time period before it was carbon positive. So not ideal, but playing with the tool, we could see some dramatic improvements to the materials and techniques. So just changing from asphalt to gravel, and that allowed porosity. That shaved about 50 years off the neutrality date. The real leap happened when we looked at including bioswales and some recycled material into the mix. And that got us into a fairly reasonable 39-year period for carbon neutrality. After that, the project would be, as they call it, carbon positive. And that means that it's going to have a net sequestration. If we'd added a green roof to this project, it would have cut it by even another 20 years. So this is where you start to see the benefits of the natural infrastructure that's really, by the numbers, it's a pretty compelling case. Okay. Moving on to functional tree planting. This is the final category I will be talking about on the practices, and that includes parks and open spaces, but we're really most focusing on street trees because they are the trickiest and in some cases the most valuable trees in the city, at least from a green infrastructure standpoint. Pardon me. So trees, I would say, are probably your best bang for your buck as a green infrastructure practice. We said that rain gardens are cheap and easy to do, but as far as the range and of multiple qualitative and quantitative benefits, trees do a lot of work, and they look really good doing it. So some of those benefits, this reducing runoff, these are all standard to all the things we've been talking about. But there's some other interesting ones, especially street trees, that they actually prolong pavement life as they're shading, they're providing less expansion and contraction. There's soil conservation, air quality, and of course, habitat and biodiversity benefits. There's also socioeconomic benefits because people like trees. So it creates safer sidewalks by creating a physical barrier along that walking edge between the cars and the pedestrians. It tends to define a zone along the edge that can be really useful for including other amenities like bike racks and benches. There's studies that show they attract up to 12% more pedestrians on average, a tree-lined street, increasing business and vibrancy and a sense of security. There's lots and lots of data around mental and physical health associated with trees, and this whole movement around biophilic design, and of course increased property value and aesthetic appeal. But these benefits are only realized if your trees are big, and large trees need lots of soil. This chart is based on research done by a landscape architect named James Urban, who found a strong correlation between soil volume and tree size. By his calculations and research, we should be aiming for about 1,000 cubic feet of soil to get trees in the range of a 16-inch diameter of the trunk, which is about the size you see on Broadway. Broadway trees are slightly larger than that. So that's just under 30 cubic meters of soil per tree, if you want to think about that in metric. And this blurry little diagram on the right here shows you what that looks like to scale. I also wanted to point out this blue line on the graph. This actually shows that as the soil volume goes up for the tree, the available water storage within that soil volume also goes up. So this is very nice kind of, correlation between the bioretention possibilities and the soil volume for tree health. So 30 cubic meters is a massive change from the practices that were pretty standard even when we started practicing in the early 90s. Here's some root balls from trees that were dug up when we were working on Rory Street. That's looking at just a little over 1 cubic meter per tree. So we're talking about 30 times this amount of soil. And of course, these are fairly large trees, so they weren't contained within that cube. Those roots had escaped and they're working their way under the roadway and other things. So that's not ideal because it can affect paving structures. It can starve out the roots as they pass underneath it, and also just generally stress out the trees. So one of the ways we can address this need for larger soil volumes is to look at things like soil cells. This one was it's called the Silvacells, developed by Deeproot. The second time they were used in Western Canada was here on Broadway. So they're kind of a pioneering application. Those ones stack together to create these void spaces under sidewalks that can be filled with planting medium, and that helps us hit those high soil volume targets. So you can see how this is a cutaway view, but the paving will go right over top of these areas, and they create nice friable open soil for roots. They tend to be on the expensive side, and utilities need to be carefully coordinated, but I would say it's now commonplace, and I'd say standard in most of the larger cities as the go-to way to plant trees on streets. Now, the soil within those will also act as a bioretention chamber, and in some situations, we've seen these cells are being used even without trees as a really great way to just work in and store water. An application here you guys may be familiar with is John Hirsch Place. So John Hirsch is, the city of Winnipeg was actually a willing partner on this project. They were interested in trying some natural infrastructure practices. So pretty straightforward. They had a system using strata cells, which are a brand of soil cells. Stormwater is captured and then directed through porous pipes down into these sort of blue zigzag here, which are where the soil cells are. And that nourishes the trees, and the soil does its magic, and eventually it'll come out the other end much diminished in quantity, cleaner and cooler. And the trees are happier. This is a couple of shots of what it looked like under construction. There you can see those strata cells underneath, how they kind of link up and create this platform beneath. These ones were selected because they're stronger than the Silvacells at the time and could support car traffic, as opposed to just pedestrian weights. So this is right under the roadway. And this is what she looks like all finished up. Here's another soil cell project. This one's under construction on Goulet. In this case, those squares are where the trees are going to be planted when it's done. And there's a trench drain that runs down the middle. And the trench drain is the way that the water is going to be infiltrating down into the cells, which extend underneath this whole median for the full length. We had originally looked at putting permeable pavers in there, but it was determined that that wasn't necessarily with the trench drain. In this Goulet project, if you go out there, it's one of the first Winnipeg roadside rain garden applications too. So the rain gardens, which weren't really in any shape to photograph yet, they're under construction. We'll see what they look like next spring. And one more quick natural infrastructure project that's not urban. We worked with the Manitoba Habitat Heritage Corporation to design and administer a special kind of shelter belt called an eco buffer, which extends about 30 kilometers between St. Francis Xavier and Eli. And the intent here was to help mitigate whiteout conditions on Highway 1 West. We all know how often that road is closed up when there's some blowy conditions. Eco buffers are kind of a unique idea or approach to shelter belts. They're intentionally diverse. They have a dense assortment of long and short-lived plants, and they are kind of sized to nest into each other and create a structurally complex community that's grows faster and has better survivability, as well as better biodiversity, habitat, and aesthetics than your typical types. So that one is, I think it's in its third year, and we might have a couple more years of planting. So another one to stay tuned on as you're driving out toward Portage. Throw a few numbers at you. Again, they should be taken with a grain of salt because they might include some American bonuses and rebates that aren't available here. The first one is that trees and vegetation can save on energy in the range of 10 to 50%. That projects with trees increase property values by 3 to 15%. And all told, every dollar spent on tree planting and management yields 2 to 5 times that investment in ecological services, which is just a fancy way of term we use for all those benefits I've been showing you. So if all this stuff looks so good, why aren't we falling over ourselves to do more of this stuff? Why aren't we just everywhere it's green infrastructure? There are some pretty serious obstacles to adoption, and I think we need to be patient. So the fuzzy definition doesn't help. There's always a bias toward traditional methods. There is still a gap in knowledge and skill within our community, and that's both on the policymaker side and on the professional side. So as I said, we're learning and we're experimenting and getting there. I think one of the biggest ones, though, one of the biggest obstacles is this one, that it crosses disciplines and jurisdictions and can involve multiple stakeholders. So when we were working with the city to try and get some of these projects involved, it's really difficult to know who's in charge. It's between parks, it's between water and waste, it's public works, it's a whole host of different people and different budgets that all have to align in order to get these things to happen. So that's a big challenge that, definitely interested in hearing your thoughts on how to address that one. And then there's other ones, the fact that it's living, we have to think about the long time horizons. There's a period that things have to establish and grow, and regulatory hurdles. It's going to be a while before these are seen, these being natural infrastructure practices, are seen as more than just an add-on. And we can start seeing them as the product that's doing the principal role and doing the hard lifting, then we're going to see some real benefits as far as costs go. So to wrap up, I want to make 3 final points. The first point is that you may have noticed that the lines between these practices are blurry. There's quite a bit of overlap and repetition in the benefits and the systems. So we can see how like green roof can also be a bioretention area. It could also be an urban forest area. And those benefits are also overlapping and repetitive. But the thing that's critical is that the way they overlap, they're complementary and they create positive feedback loops. And that's the magic of using nature, is that it tends to form these complex adaptive systems where benefits multiply and reinforce each other. So in the case of this, having the fact that forests buffer other trees from wind, so there's less limb lost and less problems of trees blowing down because it's dense, and that reinforces the ability to have strong forest cover. And same with soil health and same with property values, providing maintenance funding through increased tax bases. All these things are positive, self-reinforcing, adaptive loops that help make the system and our communities more resilient. And that, in that, natural infrastructure is really a sensible choice, because not only are they adaptive and are they resilient, they're also easier to change out and they're more flexible to adopt new things than gray infrastructure if conditions change seriously, because they're sort of lighter on the land. Second point is to learn globally and test locally. There's lots and lots of models and resources out there, so we're not starting from scratch, but we have to be careful. So here's a couple examples. These are, City of Toronto actually has details and specifications on their website. But we can't just take these and apply them. We really need to make sure that we understand our local situation, because green infrastructure is a growing system, so soil and climate are critical. So my call to action to any jurisdictions that are out there, City of Winnipeg or other municipalities that are getting interested in this stuff, is to get serious about monitoring and evaluating projects and develop standards and guidelines so we can avoid costly failures. And the final point is that it's scalable. We can think about most of the stuff I've been talking about is really at site level, but green infrastructure can be applied at all scales. The floodway is an example of green infrastructure. Bishop Grannon Greenway is green infrastructure, just like the Bioswales at Clear Spring Middle School. They're all just sort of different scales of the same thing. And these practices are at their most powerful when you're combined to create this richly connected system that links regional landscapes right down to the individual site scale. And only when we start linking and thinking in terms of systems and networks will it truly reach the status of infrastructure. So I'm going to end on a quote by Bucky Fuller. I think it applies really well to green infrastructure. Bucky said, "You can't change anything by fighting or resisting it. You change something by making it obsolete through superior methods." And with that, I'm going to thank you all for listening, and I'll open up for questions. I'm going to provide a list of some resources that I used for this and other things we rely on. I'll be giving it to Laura, and she'll be allowing it through the SBM. Are you just going to send it out as web's link or something like that, Laura? However that's going to happen? Or?
Yeah, I can send as an email to everybody, much as I sent the link out to folks today. So that can absolutely happen. And we can also include it for, this will eventually be on YouTube. And so you can just see the links below. I believe is the thing that the YouTubers say.
YouTubers.
So yeah, thanks so much for all of that incredible information, Glenn. So we're going to open the floor to questions. I'm going to get the ball rolling there with the questions. So I love the statement, learn globally, test locally. Is there something that you would just love to see come to Winnipeg and Manitoba?
Yeah, I just think I would love to see more roadside bioswales and rain gardens happen. I think we have a great environment to do that stuff. We've been doing them in Portage la Prairie. We've been doing them in Selkirk, and it's been a little bit of a struggle to get the City of Winnipeg on board. And it's just the benefits are all there. So it's an easy thing to get in, and I think it's the right sort of launching point to get these things into the public attention.
Great, thank you. All right, I see some questions in coming from people. So Mike, did you want to unmute and ask your question?
Yes, thank you, Laura, and thank you, Glenn, as well. Well, this was a super presentation, and I'm just curious, what's the possibility of destructive species affecting the bioengineered
Yeah.
Parts for the worse.
Yeah, it's a great question, because it's one of those kind of wild cards of climate change, is that we're seeing, migration of invasive pests and things that are, our ash trees are in big trouble right now. So but at the same time, climate change is creating new opportunities for different species to be able to thrive here. So I think we're just going to have to keep monitoring. We're going to see things lose, or it's going to be winners and losers through this whole process, and probably a process of testing and making sure that we're not losing track of the genetic strains that are actually have natural resistance to pests. So that's what they're doing right now in the Netherlands with Dutch elm disease. Is they're just continuing to breed and rebreed the elm trees to help create more resilient strains. And I think that's going to be another tool in the kit.
Thank you. So the next question coming in is, what do you think about using trellis structures and pergolas to replace trees? Trees are often hard to grow in city environments.
Well, they're going to provide some advantage, but I think they're going to provide limited advantage, and it's going to be just about shade and shelter. And what you're going to be missing is all this, the long list of other things that trees do for us, which is about, soil conservation and habitat. And so I think there's definitely a place for it. And one of the things we have learned is when we were working with the city on the new tree guidelines is that you can't just blanket trees across everywhere. You need the right tree in the right place. And if you want trees to have this kind of soil volume and attain the size where they're providing those ecological services, you really need to be judicious in where they're located. So in places where trees don't work, then that's certainly an option.
Excellent. All right, Bill, did you want to unmute and ask your question?
Yeah, thanks, Laura. Yeah, nice to see you, Glenn.
Yeah, you too.
Takes a landscape architect to have great pictures and really engage presentations. So
thank you.
So the very last slide, the very last point, you talked about scalability, and that's something my research is taking all of these concepts that you speak of, but trying to put it into the residential scale. So what are your comments about the challenges that, every single driveway should be a bioretention system. Every single development should have a limit, a minimum amount of trees. And of course, the right tree in the right place. How do you go from these common amenity places to the private residential scale?
Yeah, it's a good question. One of the nice things, the scalability does mean that it's easy for people to do their own thing. Like we built a rain garden with a neighbor a few years back using the CMHC guide. I had actually never even heard of them then. I should say a few years, about 10 years ago. So there's that. But the other side to this, and you probably found this in your research too, and we did when I was working with Manitoba home builders on visitable housing, which is about accessibility, is that the housing industry, particularly private residences, are pretty resistant to change. Like it's an industry that's really rolling houses out, and they're not an innovative bunch by nature. So it's going to be a tough market to have that kind of broad scale innovation being applied. Unless you can make a very strong economic case that it's worth there. And, one of the things we were talking about as a possibility is that it's an option, right? So it's something like these visitable features that you can select from the menu of options that we would like our yard to be a showcase of sustainable practices. And that's, right up our alley. So we're willing to pay an extra $2,000 to do that. So maybe that might be one way to look at it.
Okay, thank you so much. Great questions, great answers. So if soil volume is sufficient for large trees, will root ball still extend beyond that reserve? I asked for gray infrastructure planning purposes from Cindy.
It's hard to say. I think the intent is, and it really depends on how you detail it and what the area around the tree consists of. If it's going to be deep, compacted granular material from a roadbed, less likely. But if it's the native clays and we're talking about trees that are happy growing in clay, then there's nothing stopping the roots from moving beyond those soil volumes into the surrounding subgrade.
Okay, great. Thank you. All right, we have a question coming in from Ryan. If you just want to unmute yourself and ask your question, that'd be great.
Thank you. Hi, Glenn. I'm curious if you have any thoughts on any of the opportunities or challenges associated with green infrastructure as part of upcoming sewer separation projects at the City of Winnipeg, particularly the requirement that I understand that's in place for 10% of project budgets to go towards
Yeah,
that.
that's right. Yeah, and just before doing this talk, I sent a note out to the city to say, hey, what's up with that? Are you guys actually doing any of this stuff? And there are projects and plans underway, and I guess they're just kind of getting started. They're still in the planning stages, some of the ways they're looking at doing it. So I think some of the more recent road beds, they're just getting into the study and see whether that's feasible or not. But there should be no no reason not to have this as a major feature. And as you said, like the CSO study, 10%. So lots and lots of money available in the budgets to do these things. So that's really one of the most promising sides. I think we found when I was looking at it, there was a report to council that said there's not enough information to go forward to start making these decisions in a kind of a solid way. So it might mean that in order, before we can get into implementing these things, we need to do more pilot projects that are measured in a kind of a pre and post state. And at this point, we don't have any. Even John Hirsch was supposed to have measurements, it didn't. Their Green Lane test project was supposed to have measurements, and they did do it, but then they moved it, and then it wasn't the right spot. And you guys might be familiar with his background, but it's yeah, so we don't have the data to do this stuff reliably. And if I was an administrator, I'd be a little nervous about just diving in with both feet too.